Hi everyone. In today's paper sharing session, I will talk about a paper called Proteus, agile machine learning elasticity through tailored reliability in dynamic resource markets. This original work's author is Aaron Harlax, and is cooperated between CMU and UC Berkeley. This work is published in the European Conference of Computer and System in 2017. So in this presentation, I and my colleague Pato will give a thorough introduction and analysis on this work. Okay, so let's get started. So the problems the author addressed in this paper is the computation and cost efficiencies on the implementation of machine learning algorithms on shared computing clusters, which have a high dynamic resources and fluctuate market. So generally speaking, the author wants to optimize machine learning applications on the shared communication clusters. So in this work, the author introduces problems from two aspects. The first is the necessity, and the second is the difficulties. So machine learning, it's a very important topic in this decade, and more important. So it is more and more important in the not only the computer science domain, but also for some other interdisciplinary areas. So all people care about the efficiencies on machine learning algorithms and need the implementation both computational and cost efficient. So the shared computing resources is adopted by most researchers, given it's convenient and no need to buy the devices. And most users just need to train the models once and implement it or deployed the algorithms locally, so that there is no necessities for them to buy the hardwares. And the second part is the difficulties. First of all, the shared computational resources is dynamically accessible, and the price is changing based on the market. So the chances are that where the computation is not finished, the company will determined to revoke the resources, such that there will be an overhead to communicate between nodes and to store or recover the temporary results. And also, the fault tolerance is another important aspect. And also from the price aspect, the price itself is a very sensitive topic, and everyone cares about the cost. Though in most cloud and shared computation companies, they are taking the bidding strategies on the ideal computational resources, such that users can request those resources at a low cost. So as a result, the investigation of machine learning implications on the shared computational resources is an important topic, especially on the cost and computational efficiency aspect. So in the next slide, so in the introduction part, the author further justifies these problems by first they provide some prerequisites that machine learning algorithms can be implemented in parallel. So this is one of the fundamental of this work, and they illustrated this trait with three benchmarks in the wide range of domains. The first one is we can see the first is the metric factorization used in the recommendation system. And also the second one is very general algorithms can be applied onto any logistic regression tasks. And the next is latent derivative allocations, which is used in the NLP domain, or could be extended to any or some of the supervised learning strategies. And also the cost, the author also enumerated some like cloud share resources like server. So on the Amazon EC2, we can see the result from the this picture. We can see only like 2 hours executions can cost up to $100. So we can see the necessity of this work, as it can like highly reduce the cost, while at the same time keep a relatively high like execution or efficiency. And also for this paper, so the target audience of this paper um, might not be some like large companies with exclusive computational resources, but for the individuals researchers or some small scale startup companies, it is reasonable. It is like not that reasonable to buy hardware. So this may be a very interesting topic for them. And given the this work is published in 2017. It is very interesting and provisional investigations on the machine learning, because it is very it's so the machine learning computation is increasingly it's increased dramatically after that. But we can also found that though it is an interesting topic at that time, but I found that the new citations is shrinking after 2020. This, from one aspect, is that the research of machine learning is changing to like large scale models, like LM appeared recently, and some like so this cannot. So in general speaking, this cannot be trained on the shared resources, and the pre-trained models. With one fine tuning. So like researchers can just use the pre-trained models and adapt it to their own applications with few rounds of like training. So it will be reduced the computation demanding dramatically, and there's no need for like training it on the shared computational resources. And from another aspect is that the Amazon's charging policy might be changing. So if they do not take the buying strategies, and the like most of the the investigations covered in this topic will be not applicable anymore. And in the next slide, we'll talk about the motivation of this paper. So before we like investigate this specific implementations, we need to ask one question. So that is there any other solutions of the like to on the same topic? So the first thing appeared is that can we like use a single machine to train relatively large scale models? The answer is definitely no. So given the like high demanding of machine learning training process, generally most of these applications use like tens to thousands cores. So it could cost like months to years to train a large scale to train a large model. So we can see it's clearly not applicable. And for the second solutions is that we might use we can like get some exclusive computational resources. This might be true for some like, large companies, but for individual researchers or some small companies, it is also not a realistic solution. So the shared resources might be the only way for most people who might have the need of large scale training, like training models, but do not have these computational resources. And the current market provides the space to optimize the cost for such shared resources. For example, the AWS, it has a spot market for users can buy for the resources here with a relatively low cost. And the same thing happened to the Google preemptible instance and others, some other dynamic resources in like fixed function corporate clusters. Mm, but there is a trade-off. The reduced price is at the cost of the reliability of resources. So the assigned resources could be revoked if they are at some time point there are other buys give a higher price than the current payment. So uh, yeah, so that is all should be covered in this slide. And another prerequisite of this of this paper is that most machine learning libraries, so they support the parallel optimizations of machine learning algorithms like the TensorFlow or MaxNet. So in all these libraries, we can optimize the machine learning algorithms in a parallel style, so that we can when it is transmitted onto the parameter servers, we can uh, uh, yeah, we can still have the this parameterized optimization process. So in the past works, there are some investigations in this field. The first is something called checkpoint. I think it's a relatively old style one. But the problem is that it does not have a good scalability and only applicable on a single machine. And the second solution is a Spark RDD. But the uh, but in these strategies, some of the specializations is excluded, so it cannot achieve optimality. And it also only supports some deterministic operations. So I quoted it from this paper. And there are other some other strategies or approaches. For example, the current MPI, but this one seems cannot deal with the failure, so it's not fault tolerance. So there is the need for of agile some new strategies like the agile ML, which can dynamically scale up and have at the same time have high efficiencies in store and recover temporary results. Also, the shared resources. So it is since so it has dynamical so resources and changing price in nature. So reducing the price means we need to take more transition machines. And the transition machine means that we can use a spot price at a low cost to access these resources. But these machines could be revocable by the companies. So there's more so it is more likely for us to recover our data as the this transition machines is revoked. But we have other and for the but if we have more reliable machines, that means that we do not need to uh, do not need too much parameter backup or communications. But the price is to the compared to the transit machines, the price is relatively high, so we should pay it in full. So, given the context of the highly correlations of these two aspects, we can see this problem is highly these two things cannot decoupled with each other. Mm. And for the presentation of these papers, we found that even though it is a good presented in the motivations and related past work, it still have some problems. Since it does not have a preliminary sections, most of these ideas are scattered into the articles. I have to resort some other resources to help me understand these papers. I use some I check up some terminologies on the internet and some applications like ChatGPT to help me understand this paper. And before sharing this paper, there are two terminology need to be stressed here. First is the transition resources. The transition resources are some temporary resources that are only be available for a short period of time. And there's another term is overhead. Overhead refers to the extra resources and time needed to manage and maintain the cloud infrastructures and services, and communications to recover and scatter parameters.
And I will discuss the design and implementation part of this paper. So this paper resolves around Proteus. So Proteus is basically, it has two components. One is agile ML and another is BitBrain. So first we'll discuss about agile ML, and then we'll look the BitBrain later stage. So if you observe, agile ML is basically a machine learning training component. It handles the training part of the machine learning algorithms, and it tries to run that process parallelly and optimally using the required resources. So the agile ML basically divides the resources into some tier based system. So the tiers are basically non-reliable resources and reliable resources. So if we see, the reliable resources are the ones which are on demand, for which you are paying the exact fixed cost per hour. And then there are transient resources which are basically need based, and you have to pay the prices according to the spot price of that resources. So basically, Agile ML's design in the C++ library is based on a parameter server architecture. So parameter server architecture has components like parameter server, active and backup parameter server, and workers. So the whole, basically, if we see any ML algorithm, it is basically a process. I would say it's a iterative process in which the parameters are decided, and we try to find the optimal parameter value for the machine learning algorithm based on our data and our requirements. So this is basically a convergence process. You try to find the optimal values using different iterations. So this basically happens so this is like very time consuming and operational heavy process if the data is large. So this thing can be basically facilitated in the parameter server architecture. So basically parameter server holds the data of the parameters, and workers which executes the machine learning training parallelly using the divided data set. So they progress in the training, and they update the parameter values and stored in a parameter server. So this is just a high level overview. Uh, so overall, Agile ML is an advanced tool that enables the safe and agile exploitation of different quantities of transient resources and on-demand reliable resources by using different combinations of these components. Or the components of the parameter server architecture. The first is parameter server, which is a critical component of the parameter server architecture. They manage the storage and communication of the ML model parameter states, and this could be something like weights or biases of ML algorithm, and it manages these state values among the different components of the ML framework. So they basically can have different fault tolerance expectations with active and backup PSs to ensure that the training process remains efficient and uninterrupted. So next is backup PSs. Here PSs is in parameter server. So backup parameter server, they help ensure the fault tolerance and reliability by taking over the responsibilities of active PSs in case of failures or issues. So let's suppose if there's some scenario where some hardware or network failure occurs or software bug happens. So in that case, they basically take the place from the active PSs, and they maintain the parameter server values, and it basically helps to maintain the data integrity during the training process. So the next is active PSs. So active PSs is the parameter server architecture in which they receive update from workers, and they basically aggregate those values to adjust the model parameters. So this active PSs basically communicate with backup PSs periodically. So they receive frequent updates from the worker, and then they periodically, or we can say they send bulk data with back to the backup parameter server to maintain some checkpoint style system in which the data integrity remains same in case of failures. So active PSS basically help reduce trading time by enabling concurrent work by multiple workers, and they improve scalability by adding more machines. At parent servers and backup PSs run on reliable resources, whereas active PSs run on the transient resources. So if we move to the next slide, the workers and execution management in agile ML. So this slide basically gives the higher level overview of the execution flow of agile ML. So initially the ML applications can provide basically the number of or the list of transient and reliable nodes. It also provides the input data file path, which can be partitioned among workers. And again, this partition can be even or skewed based on the requirement, and then additional functions which are required to be executed, and the stopping criteria. So the stopping criteria can be number of iterations or a specific time period or validation of convergence. So now the training process on each node basically starts one worker per core and as a function of input data and parameter value. So and this whole process keeps on going until the stopping criteria. Level architecture overview of the agile ML transition process. So it is basically divided into three stages. If we see in the first stage, so there is parent server and worker at the reliable instances, and there are workers at the spot instances. And when the transition happens to the stage 2, we can see the param server is transformed to backup PS, and all the spot instances have active PSs. Now the workers are at both places, at the on demand instances and at the spot instances. Now if we say the stage 3 transition, we can see there are no workers at the on demand instances, and there are active PSs and workers at the spot instances. So this all will be explained in detail in the next slides. This is just an diagram overview of the architecture of agile ML. The higher level or the detailed overview of the stage 1, in which parameter servers only on the reliable machines. So if we see, so for all the ML algorithms, the parameter data is stored at the parameter server at the reliable resources, and the workers are at the transient node. So due to this, whenever the transient node is shut off or invoked, as they are not very reliable and they are spot instances, so they can be shut off during the machine learning training. So in that case, the in this this stage basically it does not lose the progress, as transient resources does not have a parameter server. They all communicate with the parameter server, and they basically update and read the data from the parameter server at the reliable instance. But on the flip side, if we observe, this creates a network bottleneck. So all the traffic is basically moved towards the parameter server at reliable instances, and this is basically a bottleneck and a single point of failure. So this whole idea basically holds the scalability and does not fully fulfill the advantage of transient resources. The stage 2 and stage 3 transition for the agile ML. So in stage 2 basically we have active PSs on transient machines and backup PSs on reliable machines. So this stage is considered when there is basically a higher transient to reliable node ratio. It is generally gives an improvement for from the stage 1 until the ratio is 63 to 1. So in this basically workers on transient node updates and reads from the active PSs on transient nodes. This is a frequent process, and the active PSs basically send bulk updates to backup PSs on reliable node. So, and this is basically a less frequent process than the active PSs update. So this is all about stage 2. Now if we see stage 3, so it basically says that there are no workers on reliable machines. So this basically happens to avoid the straggler effect. So what is straggler effect? Straggler effect is basically a scenario when there are one or more slower nodes creating a bottleneck, and this eventually reduces the performance of the whole system. So to avoid this, we just move the slow workers from the backup PSs, and all the workers are at the spot instances. So this way we can basically remove the straggler effect. Dynamically transitions between different stages to match the number of available transient nodes. So it basically tries to optimize the process based on the available resources. So this changes during the transitions, like basically when we transition from stage 1 to 2, then in that case we basically make change the param server to active backup param server pair. And when we do transition from stage 2 to stage 3, it basically involves assigning workers, and to the basically we assign workers to the spot instances rather than the on demand reliable resources. Now if these transitions are done with basically minimal overhead in the background, and it involves just a single worker notification message, ensuring like efficient scaling up and down of resources. There's this diagram which basically shows the elasticity handling. Now this diagram basically illustrates the scale up and scale down procedure. So now if we observe this first portion of the diagram, we have one backup PS on reliable instance, and there are two active PSs on the transient resources. So the input basically is given here that it is 40 units. So now it gets divided equally between two machines. And now if we see, like in the second stage, we have this diagram where we have backup PS on the machine 0, and we have two more additional machines which basically contributes to the data partition, and they work on the partition data. So now each spot instance runs the 1/4 of the data. So if we see out of 40 units, there are 10 units here, 10 and another 10 and another 10. So this whole procedure is a scale up. And now if we move to the third phase, now this is a basically scale down procedure. So in this, the reliable resource stays the same, but if we observe, the machine 1 and machine 2 are not there. So in this, basically eviction has happened, and this basically spot instance is basically trigger the second transitions. So this remaining spot instances, in this case we have 3 and 4, they assume the ownership of the evicted input data, and they basically handles the machine 1 and machine two's input. Here if we see 110 and 21 to 30, so now those both are now distributed among machine 3 and machine 4. And this scale down, this is basically a scale down procedure, and it has like a, and it basically gets executed with minimal delay. Procedures that we follow during handling elasticity. So the first one is scale up. So agile ML uses an elasticity controller to assign input data to available workers, and so active PSs run on half of the available resources, and when resources increases, New active PSs are started on the longest running transient resources without an active PS. So the system assigns each partition of the parameter state to a param serve and active PSs. So this basically which forwards the updates to the backup PSs that owns it and avoiding the need for reshredding. So now new active PSs contact the previous owner for a copy of the partition, and all messages are forwarded during ownership propagation with negligible impact on system preferences. So this is how like scale up procedure occurs, and in scale down basically we have resource removals. So agile ML handles resource removals differently based on whether a warning received or not. So if we see evictions refer to the removal of the resources after a warning, while failures refer to removals without warning or with insufficient lead time. So the elasticity controller in Agile ML checks for eviction warnings basically every 5 seconds, and when necessary signals active PSs to push their most recent consistent state to the backup PSs and cease the operation basically. So when backup PSs receive end of life messages from active PSs, they signal reliable workers to address, read, and update requests to them, making the process basically simple and fast. So, in case of failures, rollback recovery is basically performed depending on the number of failed resources. So, when most resources fail, the backup PSs use the last consistent state from the active PSs as the new solution state, and workers redo the lost work. So, and one more basically factor in this is that when a worker is removed from a computation, the previous owner of the worker's input data takes ownership, and input data does not need to be loaded from storage. So checkpointing is also a reliable resource can be used to account for the frequent failures, but it has like no overhead on ML training speed because there are no worker threads running on these resources, and this is basically specific to stage 3. And the elasticity controller orchestrates the reaction to the worker eviction of failures. So now in transition, if we see, so transition happens based on a ratio criteria. So this ratio is basically transient to reliable resources. So if it is greater than 1 to 1, agile ML uses stage 2, and for ratios greater than 15 to 1 it uses stage 3. The Proteus is basically bitbrain works in the area of resource allocation. So it provides agile ML the resources that it needs, and it makes the decision like which resources are we supposed to use and which resources are we going to evict to basically make the whole parallel algorithm cost efficient. So bitbrain basically decides on some parameters basically. So if we see, there is one impact of scaling which mentions that if we let's suppose if we increase the resources by x amount, then what will be the performance increase. So it considers that. Now there is also, so each resources has basically cost associated with it, and then there comes overhead when we acquire or evict a resources. So that also plays an important part in bitbrain's deciding factor. So if we see, there's this term called allocation. So bitbrain basically acquires resources with the help of tuples. So the tuple is basically instance type, count, and bit price. So if there's a set of instances are called allocation if you have the same instance type with the same bit price, and they are acquired at the same time, then it's called allocation. That's the formulation of it provides the foundation of formulation of bit-brain decision making. So if we see in this on the y-axis we have expected cost, so which is basically total work in phase, and here we have like three phases. So if we observe in the first phases, it has one on-demand reliable resource and we have one spot instance, so which has basically cost of point 0.1 and the on demand has point 0.2, so the total cost is point 0.3 for this phase. And if we observe this basically on demand instance is not doing any kind of work, and if we see here it is this spot instance is doing 2 units of work, so the total cost and works are point 0.3 and 2. So to basically minimize this cost of zero work, we basically introduce another spot instance which is at the cost of 0.05 and it is doing 2 units of work. And so now the total cost is 0.35 and work is 4. So now this has basically reduced the cost per unit work. So if we see, so this vertical line basically explains us the cost per unit work, so that has been reduced with the new two spot instances. Now if we evac the two instances, then again like this, so now we have evicted this spot instance, so now we have like cost of 0.25 which is 0.05 plus 0.2 and the work done is 2. So that is how basically bitbrain decides. So it works on the concept of expected cost and expected work. Every decision point it calculates the total expected cost and total expected work. So here in this slide we have like the formula for the total expected cost. So it's basically if you are given a set of allocations, then total cost for the given footprint is calculated as the sum over individual location cost, which is CA of xi for the whole summations. So now this individual costs are calculated based on the two things, like it is basically a multiplication of number of instances and price of that instance. So that we basically do a summation over for all the allocations and find the total expected cost. So now if we see, there is this concept called spot price trend in AWS. So basically you have two types of resources. One is on demand, which is here a dashed line, and there is this spot instances. So spot instances are allocated based on the bid price. So you provide basically upper bound of your bid price, and if the spot price at that particular time is less than the upper bound, you get the resources. Otherwise you will get like 2 minutes of notice and your resources will be evicted. So if you observe, there's this trend in the price per hour, so basically there are some spikes at some particular time. So if we observe like, so AWS basically charges for the spot instances, as in if you evict the resources before the billing hour, then you will get some free computing. So your algorithm basically has to crack some decision making, so that you basically evict your resources just before the billing hour. So that is how you use spot price trend in AWS, and bitbrain takes the advantage of that loophole. So it basically, so bitbrain basically calculates expected cost with eviction probability. So if you see here total expected cost, or this is basically a cost for the some allocation I. So bi is basically the eviction probability. So if you basically evict your resources before the billing with the probability bi, so you will not be charged, so the price is 0 and you have the number of instances, and tr is basically remaining time. So your expected cost will be basically that you evict before the billing hour plus and you don't evict before the billing hour, so in that case you will be charged pi. So that's how you cost that's how you calculate the expected cost with eviction probability and estimation. So this is being calculated by using the historical AWS spot price and big delta, which is basically difference between bid price and market price. So the historical probability of eviction is calculated with the context of eviction when the price basically rises above bid for a given big delta. So like bitbrain also has other component for decision making, which is basically expected work. So it is basically it measures the productivity from each allocation. So it computes the total useful compute time, which is delta ti. So that is calculated by minus by like, so if we observe this wi is basically maximum useful compute time. So this is till the point of billing hour. So we have this maximum compute time, and we basically minus this probability of, so this whole thing is for eviction. So when we have the eviction, so the probability of eviction of allocation j is this, and we basically multiply the eviction overhead. So this gives the total eviction overhead, and then we reduce the adding or removing resources overhead. So this is how we have the delta ti, which is total compute time. And so for calculating the expected total work, we basically multiply the number of instances with total compute time, which is delta t, which is also called expected useful compute time, and then we multiply it with the basically work produced by instance type, and we do summation for this, and we multiply that with phi, which is basically a scalability factor. So that basically denotes to how efficiently application will scale resource acquisition based on a criteria, that is basically if expected cost per work is lower than the current expected cost per work. So this is a formula to calculate the expected cost per work. So at each decision point, we have a large bid price ranging. So we tie this bid price ranges to instance types, and then we, from all the combinations, we try to find the best cost per work. So we compare this cost per work with the current spot prices, and if it is lower, then we do resource acquisitions, otherwise we don't do the resource acquisition. So this kind of algorithm can be used in a large batch computations also. So this is another application of the resource acquisition used in bitbrain, which consists of bitbrain and agile ml. So these two both are connected using zmq message specifying the application characteristic. So Proteus then connects with AWS to retrieve basically current and historical spot market data, so to which basically bitbrain uses. So with that data, basically bitbrain creates a allocation request to AWS, and AWS returns spot request IDs to bitbrain, which translates them to assigned EC2 instances. Now this basically bitbrain, with that allocation, it basically sends a message to agile ml's elasticity controller with a list of IP addresses and size of the instances in new allocation. And bitbrain basically checks for new allocation request every 2 minutes, so before the end of current billing hours, and it makes an immediate eviction. So it also monitors AWS for eviction notification and notifies agile ml's elasticity controller.
In the evaluation part, the author justifies their algorithm's effectiveness on two metrics. The first is the cost saving. It is the total cost on finishing a particular machine learning application. And the second is the runtime, which is the total time used on finishing a machine learning application. And they compare their approaches with two baseline methods. The first is combining the standard binding and checkpoint method. So this one is not effective since the binding scheme is not optimized on reducing the cost, and the checkpoint algorithm has the bottleneck of communication between machines. And the second one is using a standard binding with agile ML framework. And this one is also not effective, since the standard binding will lead to a transition will lead to the transition machine released frequently and increased overhead. The author also evaluates the scalability and did application studies on the agile ML to dissect each component and see how their method approaches the traditional one with high cost. In the first stage, they fixed parameter server number and found with 4 parameter server, the cost is still very high. And then they fixed the four reliable server and use active PS to help reduce communication bottleneck. And it shows that increasing the active PS will reduce the time cost significantly. And in the third stage, they test on only one reliable server with all active PS and find machine learning applications on the reliable one. The result shows that the time cost is close to the lower bound, which is the traditional high cost one. So overall, we can see this work as an optimization problem with dual objectives. For the time cost, the author take application studies and justify even with high ratio of transit and reliable machines, they can still have achieve the lower bound, but they did not justify the number of the ratio. And for the time for the cost, they conduct experiments on on 2 and 20 hours execution and compare the result with the standardized binding strategy. But the number is also not justified theoretically. So I can say it is a practical work. And since the author does not explore other solutions like Spark RDD, which is mentioned in the last part, so this will make this work not solid enough. And in conclusion, this work is trying to take a better binding strategies to save money on shared server and optimize the runtime and cost at the same time for machine learning algorithms. But there is also existing some works like the Flink. So this work is more like lighting up binding strategies on it. So though they take relatively different frameworks, so we can see this work as incremental contribution. But given the paper is published in 2017, and individual users might be very interested in it. So the audience is quite wide. But there is also one thing need to be noticed. The experiments are conducted in the simulation, and the experiment in the wild, the result is not released in the paper. So this seems to be a critical issue. We should be inquiring to the author. Thank you.